So what we actually have here is a type of light-activated switch. Red lights turning it on, far red lights turning it off. If you turn it on with red light and immediately turn it off with the far red light, it's as if it was never turned on to begin with. It's as if you take a light switch and flick it very quick, the lights don't manage to go on. Now, if you give the red light and then wait, for example, an hour, and then give the far red light, then you've done nothing. The red light is what it remembers. It's only if you give the red and immediately after the far red, you've switched on and off. What we have here is actually a molecular switch. A switch that's working at the level of the protein within the cell that lets the plant know when to flower. The scientists finally isolated this molecule, and it's called phytochrome. And what phytochrome is a light-activated switch. And I want to go in a little bit to the biology of phytochrome because I think it's fascinating. We can actually understand how light affects a plant at a molecular level. So what we have here is a cartoon of how we imagine phytochrome to look. And it's actually a protein which has two different components. One is the protein component here, and the other is what we see here on the top is what's called the chromophore. This is the part of the protein which absorbs the light. Now, phytochrome can absorb either red or far red light. And that's because it can be found in one of two conformations in the cells. When it's in the first conformation, which we're going to call PR, phytochrome red, it absorbs red light. When it's in a second conformation, which we're going to call PFR, phytochrome far red, it will absorb far red light. And now here comes the part that gets a little tricky. PR absorbs red light, and once it absorbs the red light, it changes its conformation to become PFR. We now know molecularly, actually, there's a slight change in the way the protein is formed in its structure, and it becomes the PFR, and that is what makes it active. I'm going to repeat this a couple times, so I know it gets a little complicated. The PFR form, it absorbs far red light, and when it absorbs the far red light, it changes its structure and goes back to become PR, and now it's inactive. So again, let's repeat this. We have the first form, which is called PR. PR is inactive. When PR absorbs the red light, it changes its structure. It now becomes PFR, and PFR is the active form of phytochrome. This would be the form that would be activating flowering in a long day plant. When PFR absorbs the far red light, it changes its structure back to PR, and it gets turned off. And so now we can see how this switch works. The red light turns it on. The far red light turns it off. If you give the flashes very quickly, you've gone up, down, there's been no effect. But if you give the red light flash and then wait a while before you give the far red, then it's too late. The signal's already been transduced forward. Now I want to qualify what I just said. I'm going to be talking about phytochrome in the classic point of view, and of course, the actual biology is a little bit much more complex. When PR absorbs red light and becomes PFR, that is the classically active form. And when PFR absorbs far red light and becomes PR, that's the classically inactive. Of course, within biology, things are much more complex, and there are examples where PR can have some type of activity and PFR can have no activity. But we're going to be talking about what's the general paradigm. What we see here is what's called the absorption spectra. This shows what phytochrome, what color of light phytochrome actually absorbs when the light hits it. When it's in the PR form, we see that it's absorbing light that's primarily in the red form. It cannot absorb far red light. The slight change in its conformation means now in the PFR form, it can absorb the far red light primarily. Now, what's important in this from an ecological point of view? When does a plant see red light? And when does it see far red light? Now, in the morning, as the sun is rising, what we see is that the sun has the light waves have a longer path through the atmosphere. And under these conditions, there's more far red light than there is red light. But as the sun rises up to its zenith, the ratio of red to far red changes such that there's much more red light than there is far red light. So for the majority of the day, a plant is seeing primarily red and not far red light. Now what happens, though, at the end of the day as the sun goes down? As the sun goes down, the ratio again changes such that the longer and longer wavelengths are reaching the Earth. We see this in the change of color as the sun as it's setting. And the ratio of red to far red becomes so low that the plant is only seeing at the end of the day far red light. And so it's actually the far red light which is signaling to the plant that the night has begun. And when in the experiment that we showed earlier, when we turn on the red light, it thinks that the day has begun. If we do red immediately far red, again it thinks that the day has ended and night has begun. This is how the phytochrome switch works in nature. Now plants see red and far red not only according to the time of the day, but also where they are in your garden or in the forest. For example, a seedling that's growing under direct light is being hit by both red and far red light, and in the middle of the day it's much more red than it is far red. But if the same seedling is growing under the canopy, under the shade of another plant, the type of light that's reaching it under this leaf is completely different. And that's because the red light is absorbed by a green leaf. And it's absorbed for photosynthesis, the energy-making machinery of the plant. The far red light isn't absorbed for photosynthesis. It goes through the leaf, and it hits the seedling growing under the canopy. So a seedling growing underneath another leaf is getting much more far red light than it is red light. How does this affect the plant? It lets it know that it's shaded, and the plant will respond by elongating in order to get out of the shade. So the red-far red ratio not only lets a plant know if it's morning, middle of the day, or night, it lets the plant know if it's in the shade. And if it's in the shade, the plant will elongate. You've seen this probably in plants in your garden, that if they're too shaded, they become long and spindly until they reach the sun, and then they expand their leaves.